In Part 7 of the Unit 6 notes, we are going to be looking at the difference between polar and nonpolar bonds and the properties of covalent compounds. In a covalent bond, electrons are shared between two atoms, resulting in a full outer shell for each. This occurs when both atoms have a strong desire for electrons, but depending on the difference in electronegativity, the sharing could potentially be unequal. The polarity of the bonds can affect the properties a covalent compound exhibits. In a nonpolar bond, both atoms have a very similar electronegativity, which leads to equal sharing. You can see that in our example here, where both sides during the tug of war have an equal number. In our example on the bottom, we have two fluorine atoms. Since they're both fluorine, they're going to have the same exact electronegativity. So the electrons are going to be shared right in the middle. Anytime you have a diatomic element, such as H2, F2, Cl2, they are going to have a nonpolar bond. Polar bonds occur when you have a covalent bond, but there is difference in electronegativity, which leads to unequal sharing. Between these two atoms, fluorine has a much higher electronegativity or desire for electrons. So while the electrons are going to be shared within the radius of both atoms, they're definitely pulled closer to the fluorine in this instance. Now, in order to show this within a Lewis dot diagram, we can draw this partial negative and partial positive charge symbol in. You might remember from the dogs teaching chemistry video that they showed what a polar covalent and nonpolar covalent bond would have looked like. In the nonpolar example, the two dogs were sharing the toy exactly in the center, whereas in the polar example, with an atom like oxygen and hydrogen, our toy would be shared a little bit more closely to one of the dogs as opposed to the other. To determine the type of bond present, you can subtract the electronegativity for each atom and determine where it falls on the following range. These are general guidelines as there are no hard boundaries, so there might be exceptions to this. If your difference in electronegativity is exactly 0, chances are you're bonding two of the same element to each other, and that will definitely be a nonpolar covalent bond. If you have a difference going up to 0.4, it could also potentially be a nonpolar covalent. The most common example that you're going to see in this class for this is when you have carbon bonding to hydrogen. Even though these are two different atoms with different electronegativities, their difference is so small that the electrons are essentially shared right in the middle. If your difference in electronegativities is somewhere between 0.4 and 1.7, it's likely going to be a polar covalent bond, where the electrons are a little bit closer to the more electronegative element. Anything greater than a 1.7 is likely to be an ionic bond. You could also just look to see if you have a metal versus a nonmetal for those binary compounds, because in those instances it would likely be ionic as well. Now let's look at the properties that you would see in a covalent compound. The weaker attraction between atoms, the single molecule structure as opposed to the crystal lattice of ionics, and the neutral charge leads to the following properties. Covalent compounds have relatively low melting and boiling points. Covalent solids are typically soft and flexible, so they're not hard and brittle like ionics. They are less likely to dissolve in water compared to ionic compounds, and if they do dissolve, they are definitely not going to dissociate. Remember, to dissociate means that they would break up into positive and negative charges, and since covalent compounds are not formed from ions, this would not occur. Because they do not dissociate, they also would not conduct electricity within water. Covalent compounds also tend to be more flammable than ionic compounds. In our example down below, we can see a compound, this is a type of sugar, dissolving within water, but it's going to be given an aqueous symbol with all of the atoms still bonded together. It's not breaking up, which would be the dissociation part of that process. A type of covalent compound known as a network solid has very different properties compared to most covalent compounds due to its unique structure. In a network solid, atoms are interconnected by a network of covalent bonds leading to a crystalline structure which is somewhat similar to the ionic compounds. Network solids may be transparent, hard, good insulators, and have high melting points. Diamonds and silicon dioxide are both examples of network solids. In this picture right here, you can see each of the carbon atoms interconnected within that structure. For our first checkpoint question, we are going to be looking at a molecule of H2. Both hydrogens have the same exact desire for electrons, so we want to identify the type of bond that would exist between them. This would be a nonpolar covalent. Nonpolar covalent bonds occur when you have exactly equal sharing between the two atoms, which of course would be the case here because we have two hydrogens that have the same desire for electrons. In our second question, we are looking at a molecule of NH3, and we also want to know what type of bond would form here. Nitrogen and hydrogen have different desires for electrons, so this is going to be an example of a polar covalent bond. In our final question, we are trying to write out properties that would occur in ionic compounds that are not typically found in covalent compounds. One example would be that they conduct electricity in water. Another example would be that ionic compounds dissociate in water. That means that they separate into positive and negative ions. That concludes part 7 of the Unit 6 notes. When we come back in part 8, we will be naming covalent compounds and writing formulas for covalent compounds.